And now, coming to you live from the great halls of Tarakas, AB Calculus. Dance. 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 Today, an alternate proof for the derivative of sine x. From section 3.5. So here's the alternate proof that I didn't give in class for the derivative of sine x. This one works off of the traditional definition of doing the limit as h approaches 0 of f of x plus h minus f of x all over h. Or in this case, sine of x plus h minus sine x all over h. Remember in Math 12 we had angle addition identities for sine and for cosine. We can apply that here, changing sine x plus h into sine x cos h plus cos x sine h minus the sine x all over h. And at this point, if I take the first term and the last term, they have a common factor of sine x, which leaves me with cos h minus 1 plus cos x sine h. And all of that is over h. And the reason I factored those first two, I can now pull out a common factor from that of sine x times cos h minus 1 over h. And then I can add to this cos x times sine h over h, which I think does a couple of interesting things here for us. But there is one little situation here. Well, let's split this up first. Sine x times the limit of cos h minus 1 over h plus cos x times the limit of sine h over h, both those limits as h approaches 0. But what is the limit of cos h minus 1? Everything else I've got down pat. We haven't encountered this yet. Well, let's take this over here and analyze this limit first. The limit of cos x minus 1 over x as x approaches 0. If I multiply the top and the bottom of this by the conjugate from the top by cos x plus 1, this will create a difference of squares on top and just a factored situation on the bottom that I can work with. On top, this creates cos squared minus 1, on the bottom x times cos x plus 1. Interesting thing about cos squared minus 1 is that this is equal to negative sine squared x, which is again over x times cos x plus 1. If I split this up into three separate multiplications, I could look at it as negative 1 times sine x over x times sine x over cos x plus 1. And I can find the limits for each of those bits individually. Obviously, the limit of negative 1 is negative 1. Times the limit of sine x over x as x approaches 0, we know what that is, and the limit of sine x over cos x plus 1 as x approaches 0, we can calculate that. Obviously, again, negative 1, this limit we know is 1, and the limit of sine x over cos x plus 1 as x goes to 0, well, sine x is 0, cos x is 1, it's 1 plus 1, negative 1 times 0 gives us 0. Bring that back over to here. We've got sine x times 0 plus cos x times 1. And then tidying this all up, that's just 0 plus cos x. So the derivative of sine x is cos x. And there, shade in the box because our proof is over.